can need to get water. And you say I is doing something, like something. Well, to be fair, that you say I know how to say, the left side, or, yeah, what am I even trying to say? I think I need to chat.
So for that one, we ask for the conventional nations, which are the event tubes. It's a sequence of bounded boxes among the frames with triplets labeled age and action location. And we also ask for the textual description. So for example, here it's for people where pedestrian is moving away on the left pavement. The exact textual description when the pedestrian on the left pavement is walking away. This is the team that won. They are from Lenovo Research, and when they come to the presentation of the solution, they provided both conventional textual annotation and the textual annotation had a period to judge, so according to that period they invited them to give us the presentation.
The leaderboard, there we go. Taking a little break. Turning on the mic and keep on.
I'm going to take some interviews. Okay. Where is that guy? हाँ आ जाओ. Come one boy. हाँ इधर आएगा. चलो एक इंटरव्यू लेंगे जल्दी. कुशवंत इसको बोल दो कि ये एक ही माइक है हमारे पास. उधर भी लड़की पड़ा 10 मिनट इंटरव्यू लेगा. क्या मैं समझा नहीं, मेरे पास नहीं है.
conosco i ragazzi che hanno fatto il catamarano.
कौन सा वो गाड़ी एकदम से वाइट रखने का चाहिए रखने का
since there are people there, I think it's not likely to happen. Oh, there is another one.
واحد يركب وراهم.
പരിപാടി അങ്ങനെ വെക്കല്ലേ കാക്ക വർക്കോ ഹലോ ഹലോ
ശ്യാമാടിനായിട്ട് നേരെ പിറ്റത് കൊടുത്തോ കയറ് വന്ന് പോയോ എന്താല്ലേ ഒരു തൊഴിലുണ്ടായില്ലല്ലോ വന്ന് 2-3 ദിവസം ഇപ്പൊ ഒരു വിളിയില്ല ഒന്നുമില്ല. ഇപ്പൊ കായ് കൊടുക്കാൻ നോഫല് മറ്റേത് കാശും കഴിഞ്ഞിട്ടൊന്നുമില്ലല്ലോ. വെറുതെ സാഫി എല്ലാം ഏത് ചോറിനുള്ളൂ ഉണ്ടല്ലോ. അല്ലെങ്കിൽ പാട്ടിന് സൗദിയിലായത് ഹോട്ടലിൽ പണിയെടുക്കുമ്പോ ആ ഹോട്ടലിൽ മത്സരം ടച്ചിലേർപ്പെടുന്നു. മാസ്കിൻ്റെ ഉള്ളിൽ നിന്ന് ആരെ ചിപ്സ് എടുക്കുന്ന ശ്യാമേ സൗദിയിൽ ഇച്ചയച്ചു മുത്തമ്മ ദിഗിനെ മൂത്തമ്മ ഇട്ടല്ലേ കേട്ടോ. മോനെവിടെ? സൗദി അറേബ്യ ഷർഫി പോയോ? 2 ദിവസമായി നമ്മളെ കണ്ടിട്ട്. അതാണ് ഇപ്പൊ ഇവിടെ പറയണത്. അതാണ് രാജേഷ് ലീലറിഞ്ഞു സെലാവല്ല നീച്ചെടുക്കണം. മയമീനോട് എന്തായിരുന്നു? പിന്നെ മയമത് എങ്ങനെ വന്നു വെച്ചില്ല. എന്നാ വരുന്ന കാര്യം പറയാം. സാധനം കൊണ്ടുണ്ട്. എൻ്റെ ഇപ്പം അതിൻ്റെ പെണ്ണുകൾ അച്ചാറുണ്ട്. രസം കൊണ്ടുവരാം. പൈസ തരടോ. പൈസ എൻ്റെ പെണ്ണുള്ളത് പോയി മേടിച്ചോ. നല്ല അച്ചാറാണ് കൊണ്ടുണ്ട്. പിന്നെ കോഴി കാര്യമായിട്ട് കൊണ്ടുവരും. പറയാം പൈസ തരാം. ചെളുക്കോടാ. ചെളുക്കെന്താ ചെയ്യുന്നത് വരാത്ത ഇപ്പൊ നീറ്റുന്ന സെക്കില എന്തോ നാളെ വരികയാണ്. അപ്പൊ ഇപ്പൊ അറിയണ നാട്ടിലെ അടക്ക് പോയി വിശ്വാസം ഉണ്ടോ? ഞാൻ പോയി പൈസ ചോദിച്ചാൽ എണ്ണ സൗകര്യം എല്ലാവരും ഞാൻ നാളൊന്നും വരുന്നില്ല. ഞാൻ 20-ാം തീയതി അബുദാബിക്ക് വരണോ? നേരിട്ട് അബുദാബിക്ക് വരാം. കൊടുന്നായി തരുമോ? ഏറ്റെടുക്കാനുണ്ടാവോ? അല്ലെ പണിയാവില്ലേ? അതിൻ്റെ ആള് ജാബറോടെ ജാബർ മരുന്നുണ്ട് കൊണ്ടുപോയിക്കല്ലേ. വീട്ടിൽ വായോ? കൊണ്ടായിക്കോളാം. എന്തായാലും കൊണ്ടേക്കോ. രാത്രി വന്നാൽ ഏറ്റോളാം. ജാബർ വാക്കല്ലേ? ജാബഞ്ഞ് വരുന്നില്ലേ? ദുബായിക്ക് വരുന്നില്ലേ? തണുപ്പൊക്കെ തുടങ്ങി വായോ? സെക്യൂറ ആ മീനൊന്ന് ഓർഡർ ചെയ്യണ്ടോ? നമ്മൾ വരാം. കാസിമിന്റെ വരെ രാത്രി. പിന്നെ എന്തും ഒന്ന് ഓർഡർ ചെയ്തോണ്ടു. അതുപോലെ തന്നെ ഞാൻ ഞായറാഴ്ച വരുന്നേ. അല്ലേ ഞായറാഴ്ച രാവിലെ വരാം. രാവിലെ കാലിൽ എയർപോർട്ട് വരുമോ? നോക്കി നോക്കട്ടെ. പിന്നെ ഈ ചോറേ കറങ്ങക്ക്. ഞാനും ഇവിടെ ദൂരെ ഷാർജയിൽ ഇറങ്ങി ഞാൻ കമ്പനി കൊണ്ടി വരും. പിന്നെ റൂം കൊണ്ടുപോയിട്ട് വരും. ഞാൻ സെക്യൂർ 2 ദിവസം 4 ദിവസം കഴിഞ്ഞ് പോരും. എപ്പോഴാണ് വിശേഷം കഴിക്കണേ? എവിടെയാണോ? നിങ്ങൾക്ക് നാടൻ കോഴി തിന്നാനുള്ള ഊത്തില്ലടാ. അത് നോക്കിക്കോളി, മനസ്സിലായിക്കോളി നിങ്ങൾ കേട്ടോ. നാടൻ കോഴി തിന്നാനുള്ളത് നിങ്ങൾക്കില്ല. അത് ഇങ്ങോട്ട് പോയി കേട്ടോ. ഹലോ, അസ്സലാമു അലൈക്കും. ഇന്നിപ്പോ നല്ല കച്ചവടം നടക്കണ്ടല്ലോ. നമ്മുടെ ഗ്രൂപ്പിൽ നല്ല കച്ചവടം നടക്കണ്ട്. ഏതായാലും അതിന് പങ്കെടുക്കാൻ നേരമില്ല. അപ്പൊ ഇനി പോയിരുന്നു. ഞാൻ വീൽ ചെയറിൽ കേട്ടോ. വല്ലാതെ സത്യം. നമ്മ അവിടെ പിടിച്ച് നടക്കുന്ന വീൽ ചെയറിലല്ലേ. പിന്നെ പോലെ ഉണ്ടാക്കിയ കിച്ചണല്ലേ. അവിടെ വീൽ ചെയറിൽ ഉണ്ടാവും. മനസ്സിൽ പൈസ കൊടുക്കുന്ന അറിയില്ല. അപ്പോൾ പിന്നെ ഫാറൂഖിനെ കാണുമോ ചുമ്മനോട്? ഫാറൂഖിനെ ഞാൻ കാണുന്നു. ഫാറൂഖ് അജ്മാനും ആക്കണം. പിന്നെ വല്ല സാധനം അവർക്ക് അച്ഛനെന്നൊക്കെ വലിയൊരു പറഞ്ഞില്ല. ഞാൻ കൊടുത്തു. പിന്നെ ഞാൻ കാണൂല. സാഫി കൊടുത്തോളൂ.
അങ്ങനെ ഓലെ കൊണ്ട് എന്തായാലും ഇടിപ്പിക്കട്ടെ, നോക്കട്ടെ. പിന്നെ ഇജ്ജ് വരുന്നൊക്കെ പണിയുണ്ടോ? എന്നിട്ട് വരാം. ഇപ്പം എന്തായാലും 23-ാം തീയതി 24-ാം തീയതി വരെ പണി കിട്ടിയിരിക്കും. എങ്ങനെ? അതാണ്
എന്താ സ്റ്റാറ്റസ്? ഇതെന്താ സംഭവം?
ഓഡിയോ ആണല്ലേ? ഓഡിയോ ആണാകുമ്പോൾ ഇതിന് മുന്നിട്ട് സംസാരിക്കും.
ഇതിപ്പോൾ റെക്കോർഡ് ചെയ്യണം.
ഇത് വെച്ചത് ഒരു കാര്യം
ഇത് ഇതിനെ കുറിച്ച് എക്സ്പ്ലെയിൻ ചെയ്യുന്ന
ഇതിൻ്റെ ഓഡിയോ
മുന്നോട്ടേക്ക്.
their relative performance differed at different
Okay, David. Thank you very much. The platform is yours, and don't worry, you will have 12 minutes from now. Thank you very much.
Good afternoon, everyone. It's really an honor and a pleasure to be here. Thanks a lot for organizing such an amazing conference. Today, I'm going to talk about a project that took almost 10 years to complete, and it's about autonomous drone racing and outperforming the world champion pilots. But it's not just about the game, it's about a research opportunity that opened a lot of real-world impact, and that's also what I want to talk about. But let's start with a video.
That is beautiful. One day, I dream I could achieve that. Damn.
You know that's not human.
Insanity.
I don't even know what I
so happy to see that in person. One day, I dream I could achieve that. Damn.
Every time I watch this video, I get shivers because many people worked on this project, more than 10 PhD students and more than 40 master theses over the past 7 years and longer than that. The results were published on Nature and Science Robotics, and Nature dedicated the cover to this amazing result because it was the first time that an AI outperformed a human in the physical world. Those people that you saw there were the world champion drone racing pilot, and the drone was powered by an AI algorithm and computer vision. It was a fair race, human versus machine. But why did we do it? What was the real true motivation behind it? The real true motivation was to increase the agility of robots, because robots that are agile are more useful. But there is also actually a practical reason behind all this work, which is to increase the productivity of drones. This is because multi-copter drones can only fly for half an hour. And if you want to actually increase their productivity, so their utility, they need to fly faster. And this is not just a motto. This is also what the equations show. In fact, I don't know how many of you know that, but interestingly and counterintuitively, a multi-copter drone consumes less energy in forward flight rather than in hovering. And you can clearly see this also from this plot, which shows the maximum distance that a multi-copter drone can fly before running out of battery. And as you can see, there exists an optimal speed. Where are current drone commercial companies on this plot? Well, if you look at the state-of-the-art, world-leading drone inspection companies, DJI, Flyability, and Skydio, they are not even flying at 1/3 of their optimal speed. Why is that? Because it's too difficult to fly at the optimal speed, because there is motion blur, aerodynamic effects, and more things. But we know that we don't know when, within 10, 20 years, all flying machines will be flying at the optimal speed in order to maximize their productivity. Where are human pilots on this plot? Well, they are not maximizing for productivity, they are maximizing their chances to win a race. But 7 years ago, when we started working on drone racing, I thought that by trying to gamify research, we could actually push the limits of research and computer vision. And that's why we started working on drone racing. But with the expectations that the things we developed will become useful in many other fields, from search and rescue to inspection. For example, there were several European projects dedicated to autonomous inspection of power lines and container ships with fast-flying machines. Also, wildfire prevention. There is now an X Prize $10 million challenge to use fast-flying drones to extinguish fire before it's too big, and we just qualified to enter this competition. And NASA is preparing for the 2030 Mars Science helicopter mission, where the helicopter will need to fly 10 kilometers. By the way, we are going to present 2 papers with NASA JPL and ESA at this conference in the next days. But why is it so difficult to fly drones fast? It's because they encounter motion blur, they encounter overexposure of the image, and they also experience a lot of aerodynamic effects. And these effects are very, very difficult to model. That's why it's very, very difficult to fly these drones super fast. When we started working on autonomous drone racing 7 years ago, we started working on it from the optimal control perspective. How do you define drone racing from an optimal control perspective? Well, you want to find the control inputs that minimize the flight time through a sequence of gates. What you must know is that in drone racing, you know a priori the map of the gates. In fact, even drone pilots have access to the racing track weeks in advance. This means that you can, in principle, generate a time-optimal trajectory. And this trajectory is superhuman, but only as long as you can stay on this trajectory. And that's where problems start, because there is no state estimation algorithm that can actually work at these speeds. So we had to develop new visual inertial odometry SLAM algorithms that would be able to actually have reliable and motion blur resilient state estimates. But we also encountered a problem from the control point of view. We tried a lot of optimal controllers, in particular MPC and MPCC, which stand for Model Predictive Control or Model Predictive Contouring Control, but we hit the ceiling. They all had inferior control performance with respect to world champion pilots. Why? Why is that? The reason why is because the state is computed from an onboard camera. We are talking about egocentric vision. What you see in this video is what the AI drone sees from its own camera perspective. How does the drone estimate its state? Well, it computes visual inertial odometry, but it also needs to reset the drift by observing the gates in its field of view. By observing the gates, you can triangulate the position and orientation of the drone, and therefore minimize the drift. But there is still a problem. Even if you reset the drift, you still suffer from the state estimation uncertainty, which depends on the distance from the gates. This is known as parallax effect and increases quadratically with the distance from the structure. This makes existing controllers not capable to cope with this varying state uncertainty. That's the reason why, after publishing a lot of papers on optimal control, one PhD student, Yu Long Song, had an idea. I think that if you use a neural network controller and we train it with deep model-free reinforcement learning, we are going to have a chance against human pilots. And he was actually right. Reinforcement learning here maximizes directly a task-level objective, which is non-differentiable. Now I'm going to show you the time lapse of the training, which takes about 10 minutes. Each yellow line is an attempt to actually go towards the goal, so to maximize the progress towards the finish line. So reinforcement learning works by trial and errors, by making mistakes. Therefore, it requires a lot of iterations. In this work, we required around 21 million steps in order to reach convergence. 21 million steps, and they were all done in simulation. There is no way to do this, in the physical world. Interestingly, the majority of the iterations, 90%, were required to reach superhuman performance. Only 10% of the iterations were used to learn to fly. More recently, we are going to present a paper at CORE where we show that if you bootstrap reinforcement learning by imitating, for example, an amateur performance, you can actually increase decrease the training time by a lot. So after 7 years of work, we invited to Zurich the world champion drone racing pilots, and we let them rehearse in a racing track. Important is to remember that the AI drone and the human drones were identical. Same camera, same field of view, same frame rate, same weight, same aerodynamics. Now let me show you the footage of the race. The AI won with a lead time of 0.5 seconds, which is significant because in these competitions, the difference between first and second place winner is 0.1 second. In addition, the AI won 60% of the races, 15 out of 25. But it was not enough to learn in simulation because simulation does not capture all the residual models of the real world. And here you can clearly see that there is a sim-to-real gap. You can see the difference between the simulated and executed trajectory in the real world. It's about 2 meters, which is not enough to win in the physical world. That's why the key takeaway of the Nature paper is that when you deploy the policy trained in simulation in the physical world, you need to record data in the physical world in order to learn the residual models of the state estimation, uncertainty, and aerodynamic effects. Then we use these residual models and we model them with the Gaussian process. We go back to simulation, we fine-tune the policy in simulation, and finally we deploy vision-based in the real world. So you need these rollouts in the physical world in order to transfer vision-based to the physical world and outperform the champions. Another takeaway is that reinforcement learning beats optimal control in racing for 2 reasons. First of all, because optimal control requires reference trajectories. And the reference trajectories bias the final control performance. So it does not allow discovering new robust control performances. Second of all, RL directly optimizes a task-level non-differentiable objective. And in addition, it leverages domain randomization, which allows the discovery of more robust control performances in the face of uncertainty. Now, after all this work, what chances then do we have to bring back, the safety guarantees of optimal control? Because that's a little bit what we lose with using reinforcement learning. What about safety guarantees? How can we reconcile reinforcement learning and optimal control? Well, if you are a bit expert in control and real-time control, you know that the optimal control problem is often converted into a quadratic program, which depends on 2 matrices, Q and P. And these matrices actually depend on the reference trajectory, which bias the final behavior, that do not allow the discovery of control performances. Instead, RL does not use any matrix. It directly, maximizes these non-differentiable objectives. So an idea that my PhD student Engel thought of was to put a differentiable MPC as a last layer of the MLP, and to train this differentiable MPC with reinforcement learning. What did we get? We call it actor-critic model predictive control. We achieve lap times and robustness similar to those of reinforcement learning. This is a very recent result. We do not depend anymore on the reference trajectory. We optimize directly non-differentiable objective. We can leverage domain randomization. We can leverage model prior. And because we do so, we actually require less sample complexity. The only cons is that at the moment, differentiable MPC is a bit slow. So of course, the training times can be a bit longer. So after all these years of work, was it worth it beyond just publications? It was. So we have founded the 3 spin-offs from my lab. This is Swind, which is operating in India. They are doing a cross-spraying over many, many hectares, and they're flying fast drones in order to optimize productivity. They use vision-based drones. Another company is Photokite, which builds tethered drones. These are drones that have a cable that sends energy and data over the cable. And they are the main company used in the US and in Japan for first response, so to help firefighters in presence of fires. And the third one is Zurikai. Zurikai actually was founded in 2015. This was actually our first spin-off. And here we put our state estimation algorithms that we developed for drones, for fast-flying machines. We didn't think at the time that this would actually serve very useful for augmented and virtual reality. The company was acquired by Facebook, which became Meta Zurich, now giving jobs to over 400 people, and they built the software running in the Meta Quest called Meta Insight, which is operational on over 25 million Meta Quest around the world. And many people have been asking me in the last few months, what's next after drone racing? Well, if you look further, who is actually faster than pilots? Well, birds, obviously, are faster than pilots. Birds are capable of incredible agility. And the reason why they do so is because they don't use standard frame-based cameras, but they use our normal eyes. In fact, our eyes are not frame cameras. They are neuromorphic cameras. They do not perceive the world in frames, but we have smart photoreceptors that trigger information whenever something changes, and they do so at microsecond latency. That's exactly what the event camera does. The event camera was invented by Innovation, which has a booth here at IROS, so go check their booth. They have a low latency, very low bandwidth, and negligible motion blur. But most importantly, they allow a latency that is continuous in time. So they stream information continuously in time. The cool thing is that they unlock scenarios that are inaccessible to standard cameras. For example, you can enable ultimate slam. So one problem with slam is that if you move the camera too fast, it suffers from motion blur. Here we are spinning the camera as a cowboy through the USB cable. And you can see that we can estimate the motion of the camera in a scenario where the standard camera cannot, because it's affected by motion blur. In another work, we show that using an event camera, you can dodge balls or other objects thrown at the drone with an incredible latency, just 3 milliseconds. More recently, here in Abu Dhabi, the group of Yahya Zwairi, our moderator, together with Boeing and Stratava, showed that thanks to an event camera, you can decrease by a factor of 10 the inspection time of holes in Boeing wings. And he just told me that there are several of these Cook arms with event cameras that are in the production line, that are operating every single day. Check how initially the inspection was done. Initially, the inspection was done with standard cameras that would need to stop in front of every hole and measure the diameter, 1 hole per second. Now you don't need to stop anymore. You can just swipe the camera over the bar, making the inspection time 10 times faster. Also, more recently, we showed that all this work done for drone racing and event cameras can be transferred to automotive. And we just published a paper in Nature where we managed to do inter-frame object detection. So we can reliably detect traffic participants in the blind time between 2 frames. And so I'm super excited about all this new technology. And with this, I would like to thank you for your attention and, most importantly, their amazing team, without which all these things would have never been possible. Thanks a lot.
Thank you, Professor David Scaramoza. I think the outcome we got from this great presentation and about his pioneering work in neuromorphic vision and how reinforcement learning, they are playing a major role in order to do non-differential like optimization for high speed, like what we call it, drones. So my colleague, thank you very much for the great presentation. We look forward for the discussion later. Thank you very much. Let me to introduce my colleague, Professor Guido Decron. He will address the neuromorphic again. So we are happy to hear about the neuromorphic technology. They are moving forward. AI for Bioinspired agile flights. So Professor Guido Decron, he is full professor within Delft University of Technology. He leads the micro air vehicle labs. He specializes in bioinspired and computationally efficient algorithms for lightweight autonomous flying or high-speed autonomous flying robotics systems. His research also advances in energy-efficient, neuromorphic sensing, and offers new insights into biological intelligence, like how insects estimate flight attitude. So thank you very much, and I hope your presentation will show now, and we will hear from you the outstanding work you are doing with your team. Thank you very much.
Thank you very much for the kind introduction and inviting me here today to talk to you about neuromorphic AI for bioinspired agile flight. So when we normally think about agile autonomous drones, we think about quadrotors, like the one you see flying there. And it actually has our code in it. This is our run during the last World Championship on autonomous drone racing in 2019, which we won in a very nice time. But in our lab, we also work on a very different kind of drone. And you will see it flying into the screen soon. It's a Delphi Nimble. We developed it in 2018. And here we slow it down so that you can see it, because it's mimicking the escape maneuvers of fruit flies. And although the fruit fly is perhaps less impressive than a hawk, it is very fast, because also the fruit fly was slowed down 100 times. Now, if we want to make drones autonomous, then we need to take into account the very stringent requirements on size, weight, and power. Here we have the drone that was developed by the organizers of this World Championship on drone racing. And this drone weighed 3 kilos. And it had on board a very powerful computational unit, an NVIDIA Jetson Xavier. On the right, you see our Delphi Nimble. It is much, much lighter. It's 29 grams, so it's a factor 100 lighter than that robot. And it can only carry very light processors. So we typically equip the Delphi with a microcontroller. In this case, an STM F32F4. And this has consequences. If you want to make such a light robot fully autonomous, then you cannot just follow state-of-the-art approaches to autonomy. For example, for navigation, a major approach is to use simultaneous localization and mapping. But if you use metric SLAM, then this typically requires hundreds to thousands of megabytes of memory already for moderately sized spaces. And this simply does not fit in our microcontroller. Let's look at an alternative then. Let's use deep neural networks, AI. Let's see how that will work. But also this you need to embed on your drone. And if you use typical units like an NVIDIA Jetson TX2 here, it's actually much too heavy still for our drone. The Jetson 2 is actually 85 grams, so it's 3 times heavier than the total Delphi. So we can obviously not carry or power this unit. And that paints a grim picture. How can we make tiny, agile drones fully autonomous? Is that even possible? Actually, it is. So I think most of us have some experience with this. So flying insects, they're everywhere, and they actually represent a solution to all these problems. If you look at honeybees, they're really little marvels of nature. They can land on a flower that is moving in the wind. They construct their own base station, and they do that together with other honeybees. They can fly away from their hive for tens of kilometers and reliably get back to their nest. They communicate together via waggle dances where the best flower patches are. And they take collective decisions. When there is a new queen in the nest, the old one needs to move out. I must say, with my kids, I hope to do the inverse. But anyway, so the old queen moves out, and the hive takes a decision where the new hive should be. And they can recognize complex visual patterns like faces. And they do all of this with only 1 million neurons. And that's amazing, I think, because to place it in perspective, we have 86 billion neurons in our brains. So how do they do this? Well, the key to insect intelligence is parsimony. It's the efficient and robust use of the resources. And if we look at the kind of things that animals do, I think we can do similar things with our robots. So for one, the embodiment of insects is very well evolved by nature. And if you see here, this is a flapper drone. It's a spin-off from our lab. And actually, they're present here at IROS at booth 77. And this is a demo by flapper drones. And it's flying in a greenhouse. And here it's colliding with wires. It gets entangled in the wires. It's touching the leaves. It's colliding, but it keeps on flying. And if your body allows you to do this, this is very different for drones, quadrotors. Quadrotors would just crash. But if your body allows you to do this, then that's amazing because you can lower your cognitive load. You can allow for an occasional collision. Another thing that we can also do with our drones, like social insects, is to collaborate in a swarm, to go beyond the limitations of the individual. Here you see a swarm of drones that is able to explore an unknown space, avoid obstacles, and they also have gas sensors, which allows them to sense gas, but also communicate with each other and find the source of the gas. And robots, just like animals, can make use of sensory motor coordination. What you see here is a drone that on purpose moves up and down, and it does this to induce translational optical flow. And this makes it easier for the drone to see and avoid obstacles. So in the end, mechanisms like this lead to very parsimonious solutions. What you see here is a little crazy fly drone that has a tiny omnidirectional camera mounted on top. And it can fly away for 100 meters, and then it can also come back. And it does so by visual route following, inspired by how insects do this. And it only uses a few kilobytes to do this, so it's extremely efficient. Now I think this is all very hopeful. It shows the potential of drawing inspiration from nature. But the studies I just showed, in my eyes, are still limited. And the main limitation comes from the processing of highly dimensional sensor data, like vision. And that is why I think there we need neural networks, but we don't need the conventional ones. And this is the reason that with my lab I've been investing a lot of research in neuromorphic sensing and processing. And this was already luckily introduced a bit by Davide. And so this kind of sensing and processing mimics animals' asynchronous and sparse sensing and processing, making it a solution that is extremely energy efficient, fast and lightweight. Here is another video of a normal camera versus an event-based camera. And so you can see that the normal camera cannot perceive the fast-moving rotor, but the event camera can capture it perfectly because the pixels, independently from each other, just track whether they're getting brighter or darker, and then they send an event. And in our case, we work on neuromorphic processors that can embed spiking neural networks and that also function in an asynchronous way. So these events from the vision go into a spiking neural network, which is much more similar to the neurons in our brains. These neurons have membrane voltages that change over time, and when they go over a threshold, then they send spikes to each other. And these are binary signals that are easy and quickly to process. Now, when they invited me here for this presentation today, they asked me, what is my vision? Well, my vision is to provide robots with fully neuromorphic AI to make them autonomous. And I think if we want to do this right, we should make an entire autonomy stack. We should embed the entire autonomy stack into a single neuromorphic chip. So this means that we need to perform all tasks we do on a robot in this neuromorphic chip, from low-level attitude control to high-level navigation. And this is an enormous challenge because spiking neural networks are still much harder to train and deploy. And when you think back of the start of my presentation, we were drawing inspiration from the strategies followed by insects. But what I think is really exciting is that when we put this full solution in such a neuromorphic chip, we get much closer to nature's solution also on the algorithmic and hardware level. So where are we now? This year, together with my team, we published a paper in Science Robotics on the first drone being controlled with a fully neuromorphic vision to control pipeline. So you see the drone flying. It's a little bit small for you, I guess. And so it's flying, it's controlling its ego motion. It can move in any direction. And it does this with an event cam that is looking downwards at the floor. And if you look well in the video, you see the events on the bottom left, and then you see these like black squares with white dots. What are those dots? Those dots are the spikes in the spiking neural network. This spiking neural network receives the events, processes them to determine optical flow, and still within the spiking neural network, it transforms the optical flow to control commands for the drone. So on board of this drone, we have an Intel Loihi neuromorphic research chip that implements this spiking neural network. And the question may be, can we now start delivering on this promise? And that's why we ran our network, which is a 5-layer network with roughly 30K parameters. We ran it also on the NVIDIA Jetson Nano. And if we then look at the execution frequency, it's always 25 hertz. They're quite consistent. And then the power is 1 watt idle power and 1.9 watts for the inference of the network. So 2.9 watts in total. If we look at the Intel Loihi, it runs between 274 hertz when there's many events to 1674 hertz, so really fast when there's fewer events. For example, if there's less texture. In terms of power, it has a comparable idle power, 0.9 watts. But for inference, it only uses 7 milliwatts for this same network. So if you can cut down on the idle power, then you can get a solution that's like a factor 100 more energy efficient. But with current technology already, we can show it's 10 plus times faster and 3 plus times more energy efficient than common solutions. Now you may be wondering, weren't we supposed to talk about agile flight? Well, low latency, these fast execution frequencies are extremely important, of course, for fast flight. And what I want to show you is very recent work that we just submitted, in which a drone is controlled by a neural network, and this network directly maps the state estimate, things like position and velocity, to raw motor commands to fly in an almost time-optimal way. And so you see the drone flying really fast here, and it's important for our fully neuromorphic solution that everything is done in a neural network up till the motors. And that's very different from other existing work, because there a neural network is used, but it still relies on low-level controllers to cross the reality gap. Here the network does everything until the motors. So, I think neuromorphic bioinspired AI will be key to agile autonomous flight and to autonomous robots in general, because all robots are limited in terms of resources. But, and this is something that makes me very enthusiastic, if you draw inspiration from biology, then you can also learn about biology. And I want to give you 2 examples of this. So one example is that I looked in the literature about how biologists think that honeybees land. And I implemented that in this robot. So biologists said, okay, honeybees keep the optical flow divergence constant. But you see what's happening here. If we implement that, the drone never lands. It starts to oscillate close to the surface. Why is that? So I'm not going to give you the details because of the very limited time, but we found out that this is not a problem. It's actually a way in which also insects can know that they arrive at the landing surface. And so these oscillations are properties of the optical flow control system, and they allow these insects to scale their monocular vision. And a final example is this one. This is a century-old problem where biologists were wondering, how do insects know the direction of gravity? How do they control their attitude? In drones, we know. In drones, we have accelerometers. They measure the acceleration, and this allows you to determine the gravity direction. And you see on the right a normal drone flying and controlling its attitude with accelerometers. But biologists never found a sense of acceleration in these insects. So they were wondering, how do they do it? And we showed both theoretically but also on a real drone that you can determine the gravity direction and control your attitude with only optical flow and a model of your motions. And you see on the left a drone that uses this technique. And what I think is very cool is that it works. It's actually very reliable, but it wobbles a little bit. It wobbles, and that is very similar to what we often see of insects. Now, before ending, I would like to thank the huge research team that is behind all of these studies, all these people that worked so passionately on this research. And I want to thank you for your attention.
Thank you, Professor Guido Decron. And it's inspired like a presentation. Excellent to see how bio-inspired systems that we learn from Also, I am like more than happy to see how we are moving toward a neuromorphic chip and neuromorphic processing, how spiking neural network should be on board in order to get best out of a neuromorphic in terms of energy efficiency and in terms of speed. Thank you very much. Thank you. So the third speaker with us today is Professor Giuseppe Luiano. He is a professor within the New York University and director of the Agile Robotics and Perception Lab. He is focusing on autonomous robotics systems. He previously worked at the GRASP lab at Lynn University. His expertise including perception learning and control for autonomous systems. He received several prestigious awards. We would like to welcome him to the stage and to hear from him the interesting presentation. Thank you very much.
Dictation, you want that dictation? No, no, no. This is the... there is no display. It's PowerPoint. I mean, this is original. This is original connector. Why is not working? What do you mean it's sure, give me the USB.
for example, a commercial model that I think is nice to have a look at. It's a SynSense spec, and it has a size factor, basically the size of a fingernail, which has an event-based camera and a 9 convolutional layer spiking neural network. And this is the kind of solution that we would like to see, and then we would only want to use this chip and no interfacing or companion computers, because this may make you lose the kind of advantages that we want to reap from this approach.
Maybe I have a question myself, please, if you allow me. So how can neuromorphic computing with SNN transform real-time decision-making in dynamic environments for high-speed machines? And are we close to this breakthrough, or we need more time, especially for big things at high speed? Yes.
Yeah, the challenge with dynamic environments is that with the neuromorphic sensors, like event cameras, in principle, every pixel is triggered if you are in a very textured environment. But this is actually wrong. In fact, what happens is that the event rate is proportional to the gradient of the texture and to the relative speed and the relative depth. So effectively, you can actually modulate the threshold, so the contrast sensitivity of the event camera, in order to only be sensitive to strong gradients and objects that are actually only moving relatively to the drone at a relative speed. So basically what you can do is by looking at the temporal statistics of the events, and by doing so you can actually enable things like dodging objects, like objects thrown at the drone and other things, or many different things that are moving at the same time.
Thank you very much. Maybe a last question, I hope, before they will manage to get these things. So you mentioned in your presentation that RL beating optimal control. And maybe people from the classical control paradigm, maybe they think otherwise. So how do you defend your point at this?
Yes, thanks for the question. I was actually presenting this same work at the NMPC conference, where there were 200 experts on nonlinear model predictive control, but it was quite intimidating, but in the end they understood the reason. So the point is that I'm not saying that RL beats optimal control in everything, but just at racing, robot racing, car racing, drone racing. And the reason is because these are basically tasks where there is an objective function which is non-differentiable, okay? And so RL basically directly solves for this non-differentiable objective function, while optimal control requires always the reliance on a reference trajectory. We tried to actually work on economic MPC, so that's what the MPC community will tell you when you present this work. What about economic MPC? So in economic MPC, basically what you're trying to do is to relax some of the terms and, for example, the reliance on the reference trajectory. The way we did it is with our paper called Model Predictive Contouring Control, where we start with an initial guess of reference trajectory, which can be a straight line trajectory, and then we loosely follow this trajectory by adding an additional term to the MPC objective function, which is the progress term, which maximizes the progress towards the finish line. By doing so, basically, you kind of find a trade-off between following this approximate reference trajectory and also maximizing the progress. But still, the problem is that the control performance was below that of reinforcement learning. And the reason is because also there is still this reference trajectory eventually that is biasing the final behavior. And second of all, the absence of domain randomization. So with this latest work we presented at ICRA called Actocritic Model Predictive Control, we try to bridge the gap between RL and MPC by putting a differentiable MPC in the last layer of an MLP, and then we train it with deep reinforcement learning.
Thank you very much. Please, also we can take further question, please, from the audience. Yes, please.
Thank you very much for the great work. We've seen a lot of development in sensing technologies and trying to apply controllers on low-level and constrained hardware, and hopefully we'll see great development 10 years from now. But and applying reinforcement learning to model or capture the unmodeled dynamics and compensate for them in the controller. But my question is, what happened to the basic physics? Are we giving up on understanding physics well, understanding aerodynamic effects and turbulence and all these edge cases, or are we ever going back to that route or not? I want to see your view on that.
The question is when you translate everything to neural network.
Thank you.
In physics and models and so on, you want to go first?
Yes, please.
So it's definitely challenging, right, to put everything in a single neural network. But yeah, we don't give up everything that was done before, obviously. But we do need to figure some things out again. And I think one of the things that's important to say is that when you train a neural network, many people see it as a black box afterwards. Like, yeah, it's a black box. It works, but I don't know if it generalizes to a new situation. But you can actually, of course, analyze these networks. So in my eyes, they're actually white box. Because we can only run them on chips because we know what all the elements do. It's just that each neural network is a small complex system, or sometimes a big complex system, consisting of many local elements. And if you study what these networks learned, and you can actually do this in various ways, then you can still get back some of the understanding that you need to also see if it generalizes. And the same thing goes for like physical constraints. You can embed these in the network, for example, in a physics-informed neural network approach. So you can use this kind of approach if you want to influence the solution more by physical constraints.
Thank you very much. I think with those questions, we need maybe to move to another speaker. If we still have problem on this, I hope it will be solved. Yeah?
Okay, great. So I think we're ready to go.
Yes, thank you.
Technical problem solved, so thank you. Sorry for the delay. And thank you for the invitation. So today I really want to present a little bit the work that we have done on agile and collaborative flight. So let me start from a couple of videos that really show the success in this area. About 10 years of work, basically people started working from planning and control, if you think about 2010, to the inspection of Fukushima reactor, basically in a dark environment. And more recently, there has been a lot of research on human level performance. At the same time, we've seen a tremendous progress also from the industrial perspective. So drones were basically used for photography, then even more with Skydio deployed in really unstructured environment. And no one would have thought that after in 2022, basically 2021, 2022, basically the drone could be deployed on Mars. But what are the society needs? So if we see what's happening basically in all the application areas, going from search and rescue to COVID-19 outbreak up until the delivery in urban environment, we see that there is a need not only for agile machines like the first speaker mentioned, but also for collaborative machines that are able to collaborate with each other to speed up the task execution, as well as to basically increase the resilience with respect to robot failures. And the way I see the future, I see robot machine fully interconnected with basically all others autonomous machines in city-like environment, and basically learning from each other. Despite the great success, there has been also several challenges. So if you see here, basically when we go in unstructured environment, pretty much the algorithm that works very well in the lab just don't scale. And if you see, for example, the DARPA Subterranean Challenge, great success, great project, but at the end of the day, robots are still extremely slow, and deploying more than 2-3 robots becomes extremely hard. So what are the challenges, in my opinion, that need to be solved to basically go to the next autonomy level? If you think about it, it's along 3 axes. So on one end, we need better, more efficient algorithm. Then we need to take care of adaptability and safety. And on the third axis is really scalability, so with respect to the number of robots and also with respect to the types of environment. And what I'm going to present, in the next, hopefully 10 minutes, it's basically, that the idea is how can we go beyond the traditional autonomy paradigms for efficient, adaptable, and scalable aerial navigations. And there has been a proliferation of machine learning algorithms, at the perception control level. So where do we need to use this algorithm and where it's really useful and how? At the end of the day, we want to maximize each one of these axes to have basically a system that is efficient, adaptable, and scalable. So we start with some of the work, that we have done. And the key idea behind is really, in my opinion, that we need to learn models and representations that are meaningful and could be used, in an optimal way in the decision-making process. So these models and representation needs to be efficient and safe, which means, lightweight and interpretable, and needs to be scalable with respect to multi-robot systems. So basically, not only distributed, but also robust to intermittent communications and potentially being used in multiple tasks. We've done some of this work, for example, in this case where we show continuous adaptation. So there is, an optimal controller that acts on neural dynamics. So we completely learn, in this case, the dynamics of the system by injecting some physical knowledge into the learning process. And the system can continuously adapt basically by comparing the unroll trajectory basically of the optimization with respect to the state estimate, and continuously adapt the model in a way that you can handle several uncertainties. For example, a mass increase, mixing different propellers, or even wind disturbances. So you can see that the robot is basically, the model is trained basically on the single robot, and by adding a payload, the system is able to continuously adapt to these different types of system and disturbances. Similar, with Bootstrap, the robot with 4 different propellers, and you can see that the system stabilized quite well, learning basically this new model, these new parameters, these new propellers that has never seen basically before. In addition to that, we can also, embed in this kind of predictive control some kind of sensing and perception constraint. So, for example, for safe navigation. So, in this case, we combine a foundation model from, a visual foundation model that provide monocular depth to identify basically the collision, the points in the environment that basically could generate the most probable collisions. And we can basically, allocate this kind of constraint in a dynamic way into control barrier functions directly in the model predictive control. And this provides basically the ability of safe navigations. And you can see that, the performance are quite amazing, and we can navigate basically without building an explicit map of the environment. You see basically what's happening, that basically the collision points get selected dynamically into the predictive control basically approach. And these are some of the tests that we also did in lab environment. So the drone is not really building any type of map. It's purely reactive collision avoidance. Blackout. I don't know. It doesn't depend on me. It's like,
Please, about decentralized control for heterogeneous multi-robotic systems.
So that was I gonna present basically. So the idea behind was, that you could streamline basically an optimal controller to the help of reinforcement learning by approximating basically an optimal controller with a neural policy which can run even on really small, tiny devices. at the rate that's, comparable to the one of a DSP processor, basically. So that's the overall idea. Or maybe it's coming back. Let's see. No.
Okay. Maybe the other part, you are working in GNN toward this.
Yeah, so, what I was going to show is that, the idea is, here we go. So we are back on track, so that's great. So if they can project this, hopefully we can. Great, so sorry again, it doesn't depend on me. So the idea is that, we basically modify the cascaded controller with a purely model predictive control approach, and we can leverage, the learn model and other type of sensing and perception constraint. But this is very difficult to run on this really small scale device. So what is possible to do in this case? In this case, the idea would be to approximate, the MPC with the neural network policy, that basically map directly from state to motor inputs, basically. So this is a work that, we just published this year, and pretty much we address really the reinforcement learning challenges in this type of architecture. So basically, we address the problem of prohibitively long training time and of the sim to real, basically, gap. I want to focus, on the first part, which is prohibited long training time. There's been a great collaboration, with the TII in Abu Dhabi. And the idea here is that basically, we achieve this in two complementary ways. So the first one is that really we implement some kind of curriculum learning. And the second really element that contributes to this achievement is really the ability to have a super fast library, which we released, which is RL tool. It's actually, several order of magnitude faster than other, existing deep reinforcement learning library. It's based, already configured with several simulation environment and has already several reinforcement learning algorithm, and it's completely open source like in the other algorithm. The other thing that I want to mention is that, we have extremely, small training and deployment time, and you can potentially, also train on a small, microcontroller. Then the last part, we can train basically in 18 seconds, and after 18 seconds, the task was mainly to hover in place, but we also see that it generalized quite well to trajectory tracking and to rejection of disturbances. Then the last few minutes, I want to focus really on how these models and representation could potentially scale, to multi-robot systems. And here we have used quite a lot, some graph neural model that are quite useful, because they're inherently distributed and they allow to exchange information, compressed information between the agent. And really the idea is to collect and fuse in intermittent information in distributed fashion to achieve accurate and resilient context-appropriate decision-making. So the idea is that each robot has, some kind of latent representations that get shared, at multiple levels between the different robots. And we have shown that this works pretty well, for different types of tasks, both at the perception level and also at the planning level. So for example, in this case, you can see that the task is monocular depth estimation from multiple views, from multiple aerial vehicles. And one of the robots is completely affected by noise or by, disturbance, which could be an adversarial attack. So you can see that the single robot by itself is not able to really solve the task, but while collaborating with the others, basically, and exchanging information, is basically, able to reconstruct the entire view. So you can potentially even see through the walls. Another work, that's going to be presented at this IROS tomorrow, basically combine the graph neural network that is used for task planning, for task assignment, with, for example, nonlinear model predictive control to achieve safe navigations in the environment. And, this safe navigation at the NMPC level also consider the detection range. So both in terms of communication and in terms of, ability to detect the obstacle. So we really use basically these learning techniques at the high level and combined with low level optimal control techniques for, with guarantees, basically. And these are some of the video that also we show in the lab where we really show that the 3 agents respect all the physical constraint and the distances both between the objects, between each other and between the objects in the environment. So to conclude, basically, the key takeaways to boost aerial autonomy is, in my opinion, learn efficient models and representation that can be exploited to guarantee safety, adaptability, and scalability. Instill physics knowledge in this kind of models and representation is generally very useful to facilitate generalization and interpretability. And reinforcement learning can reduce really the complexity and the deployment time. In terms of what's next, I think there is lots of work to do in models and representation that really unify the perception and action part. In task relevant, basically models and representation to share basically only features between the robot that are really relevant to the specific task so that you can comply with computation and communication restrictions. There is a lot of work to do in multimodality, so how you exploit the different sensors that are available on robots that are potentially heterogeneous, both in terms of mobilities and in terms of sensing modalities. And then also how you guarantee safety at, both at the planning and the low-level control. I want to thank all my students that contributed to this journey and all the sponsors, and thank you, and I'm open for questions.
Thank you very much, Professor Giuseppe. I think the next presenter, he is online with us, Professor Mirko Kovac, and I have to keep him in the loop using WhatsApp. Thank you for the great presentation. Thank you. In order to let him know what's happening and why the delay. So I hope he will be now sharing his screen with us, and we will hear. I can see him now, please. Hello, Mirko, can you please share your screen with us?
Yes, thank you very much. I will just share my screen, one second.
First of all, Professor Mirko Kovac, he will speak today about drone for environmental health. He is Director of Aerial Robotics Laboratory at Imperial College London, also leads the Laboratory of Sustainability Robotics at EBFL. His research focuses on developing mobile robotic systems for sensing and autonomous manufacturing in complex environments. And he has also the physical intelligence like terminology for designing a new concept of robotic systems. Please, the platform is yours. Thank you very much.
Thank you very much. It is my great pleasure to be here, and thank you very much for the invitation. It's a great honor to speak to you today. And so what I would like to talk about today basically is about how we can think about creating lifelike, almost biological robots. And of course, if we want to do that, we can learn a lot from nature. And in nature, we see that, for example, bees can interact extremely well with the environment. They can do all this amazing agility, as we have seen by the previous speakers. And there's a few things that they do. So one is that they combine sensing, control, navigation, as well as unsteady aerodynamics and the different materials, structures, and actuators in their bodies. So they don't contain rigid, solid materials and then do some level of control on it. They actually co-evolve all of these aspects, the sensing, control, and actuators. And in fact, the muscles even have the sensing embedded in them and the control as well. So this is another way of building them, or how they are built compared to many of our robots. Now, if you think about robotics and we think about the task of landing on a surface, for example, we can of course do that with a lot of navigation, control, reinforcement learning, vision, and so on, as we see on the right side, where we can even model the pitch-up maneuver using unsteady aerodynamics and so on, and then land on the surface. But if you look at how this is done at small-scale animals, we see that they use a lot of their body to do this. So they use antennas, they use their legs, they use their physical embodiment to really help them to transition to the surface. And I think this combination of the digital intelligence with control and sensing and so on, and the physical intelligence or mechanical intelligence is the key to create those lifelike robots. So the mechanical aspects or the promise of soft robotics, if you want, as well as the promise of AI on the right side. So if you combine the two, then we really as a community can create lifelike robots. Now let me give you a few examples of how we think about that and some projects where we apply this philosophy of building the robots. Now the first one I would like to share today is the idea to use robots that would do aerial additive manufacturing. This means that they are flying vehicles that can 3D print structures from flight and collaborate with ground robots, with climbing robots, with humans, and like this build structures in inaccessible environments where the big 3D printers cannot be brought on site, or where the size of the structure should not be constrained by the size of the 3D printer. Now, we are working on this project for about 8 years now, and the robot that we built looks like that. So it's basically a flying vehicle that has a base platform using a model predictive controller, then has a delta manipulator that stabilizes the extrusion head with a precision of a few millimeters, then can then extrude material, in this case cementitious high-performance cement material, to create layers of materials and like this 3D print structures. Here in this example, 27 layers using cement materials. Now the key here is to evolve the materials in such a way that they can be extruded and hardened fast enough, but also are soft enough to be extrudable, while the embodiment, the architecture, the behavior, the control and the autonomy, as well as the multi-agent coordination is co-developed in order to achieve this and allow us to develop different construction systems, so different building structures. So this is summarized in the framework that you see here on the right, on the bottom right, where really it's about the quality control as well as the scanning in the loop to then assess what needs to be built, how it needs to be built, and how the change of the environment can enhance the next building step. And this change of the environment or the adaptation to what has been built already, I think is really one of the key steps. Because if you have a material that is hard to predict, like this polyurethane foam in this example, it's very difficult to build something very precise with it. So the precision comes not just from the extrusion head or from the robot flight behavior, but also from the behavior of the materials. Because of that, we here included a scanning drone that can 3D scan the structure, and then based on the 3D scan, we can extract the ridge line and inform the next extrusion step. Like this, we can make layers of materials very in a scalable manner, even though each layer or each process step is in itself less precise. This is something used very much in nature. It's called stigmergy, where the change of the local environment allows us to take decisions to build the next step, and like this have a scalable construction principle. Okay, so another example that I would share with you today is the idea that we have drones that can fly inside of fire or very hot environments. So robots that are temperature agnostic. The robot we built looks like that. It can basically fly inside of around very hot environments, around fire, but also in very cold environments, as you see on the bottom right, where we tested it in a glacier in Switzerland. The key is to have the morphology, so that the design of the robot being adapted to this. So we have a CO2 cartridge for internal cooling if needed. We have also the motor arranged in the center of the drone rather than at the periphery. And most importantly, we developed a new type of polyamide aerogel that is fiber reinforced. And like this can allow the robot to be, one, temperature resilient, because it's a very good heat insulator. But second, it is building the structure. So the structure of the robot is constructed from this aerogel. And like this, the aerogel can be really the part of the embodiment of the robot. Okay, another example I would like to share today as well is this idea to have robots that can move in air and move underwater. This is something that we work on for about 10 years now as well. We have various, so we have this book here that came out, and also various collaborations on that topic, also with a new project that started last year. And the overall vision is shown here, which is basically being a metamorphic vehicle that can change its body structure and have soft materials and onboard adaptive controllers to allow it to transition through different environments. Now, one example you can see here, which is basically a flying fish-inspired robot, which uses high impulsive thrusters or high impulse thrusters to eject itself from the water. In this example, it uses calcium carbide, which reacts with the environmental water, creating acetylene gas. And this then can be ignited to eject the water like a piston from the body and boost the vehicle out of water. So this is basically an aquatic robot that can overcome obstacles by jump gliding out of the water. So here you see the jet, then you see the spray, because it's mixing inside of the body, and then the gas jet, and then it jumps a distance of about 23 meters using 0.3 grams of calcium carbide that it carries on board. So combustion, and here again, using environmental conditions or environmental materials can be a very powerful method to transition between terrains. A second example is the idea to do sailing motion. So can we use robots that would not just fly or dive underwater, but then could reconfigure, and through the reconfiguration could allow the robot to use low energy locomotion in aquatic environments. So in this example, we built this robot from scratch with the manufacturing, with the models, and with a sailing controller that can switch between the flight controller configuration and then transition in a sailing controller mode to then allow it to sail on lakes and in different environments. Now the key here is that it is less invasive than any other kind of manual methods of environmental sensing. Typically you would go there by a boat, with a boat to measure water quality or measure biodiversity, but this vehicle here was designed specifically for that, to access the area, but then use minimally invasive, so low energy and low noise modalities of motion to interact with the environment. Now, this is actually also what I would like to emphasize for how we can think about impact in environmental sciences. And I think this we can do here with various robots, but as an example, it's the SailMath, where we can think of a new concept, we can then model this, develop it, test in the laboratory, publish in engineering journals, and then do the auto-validation, but then do this with an environmental sciences question in mind. So here, for example, what we did is to use sound measurements, so a soundscape analysis, to measure bird species inside of a protected lake in Croatia. We did this twice, once in winter, once in summer, across different seasons, and we measured how many birds there are, which species there are, and like this could quantify the species and how the protection of the area could protect those species and actually increase biodiversity. And I think this methodology of posing the question in environmental sciences with the robotics question of design, I think can be quite powerful and create a lot of nice impact. Okay, so another example, last example today I would like to share is the idea that not just robots cannot be just vehicles to collect data or sense the environment, but they could act as fully lifelike robots that sense the environment and then integrate into a natural life cycle. So they measure the environment and then biodegrade, so they die and then awaken again or grow again and fly again or operate in the environment. This is something that we call transient robotics, where, let's say, the robots are not just being manufactured and used and then thrown away, but rather being applied and biodegrading and then can regrow using different microorganisms or biohybrid components. Now, we are working on that also for a while already and try to develop the manufacturing methods to build the foundations of such robots in terms of sensing, actuation, and structural performance. Here, just to give you one example of one thing that we are working on, which is a biohybrid cryogel composite manufacturing. This means that we use microfabricated cellulose and combine this with, for example, gelatin or starch, and then can create those type of molded structures that allow us to make those porous materials, which can have certain performance characteristics alongside certain biodegradation characteristics. So they need to perform well when they need to be used for the robot and then biodegrade as we want later on once the robot usage is done. So by tuning this type of manufacturing process and developing new materials alongside with the robot behavior and mission, I think then we can, if you do that correctly, then I think we can have a very promising base technology for environmental sciences and natural health. Now, coming back to the philosophy of how do we build such robots? So what is our way of thinking or our design approach? And so, as I mentioned alongside the few examples, one important aspect, I think, is the idea to co-develop these technologies and the material science, the robot control, the robot morphology, embodiment, and so on. Now, this is important because it shouldn't be a linear step of starting in simulation and then ending up eventually in the robot, but really trying to co-evolve all these different aspects and posing the scientific questions at the interfaces of these different disciplines. If you do that, and that's my hypothesis, if you do this correctly, and then we can create those lifelike robots that are really having similar capabilities like living organisms. Another aspect which I think is important is how to do bio-inspired design. And it's very easy to say, like, nature works like this, so I build a robot that kind of looks similar. But I think the key is to really be very careful with this and try to take inspiration, analyze natural systems, but then very quickly home down on what the functional principle is that nature uses, and then use this principle to build it into the robotic system using the best of engineering knowledge. So by expressing these principles as clearly as possible, we can create robots that are bio-inspired, but also are better because of this, and don't just look alike some living systems. Okay, so to finish, I would like to just add one more element to the discussion, which is the usage of, or the need for testing infrastructure. And I think there are a lot of indoor flight arenas around the world. So we also have one here at EMPA in Zurich, at the Material Science Institute, where I have the lab. But also there are many outdoor facilities for testing. One thing that is missing is basically a gap between the two. So outdoor environments which are extremely well instrumented, where we can test and validate novel robotics ideas. And this is something that we are building, which we call the Drone Hub, and it's a testing platform that should be accessible for researchers around the globe. It will have three innovation elements. One is a facade for 3D printing and repair, where robots can interact and manufacture different environments. The second one will be a biosphere, where we can test and validate how robots would biodegrade and place sensors for environmental sciences questions. And the third will be the facade of the building, where we can test how robots can live and be residential systems in those environments. So the structure you see here in front is our headquarters, where currently the lab is in, and we are now expanding this with the Drone Hub flight arena for validation and showcasing of some of the projects. So this is not a fantasy, it's actually already being built, and we open it formally in about 1 month. So with this, I would like to thank all the funders that have supported this, and also the team who has worked on this for many years. So I'm very thankful to everyone involved. And as a next step, I would say that I think there's a long way to go on the interface between material science, soft robotics, and aerial robotics, combining digital and physical intelligence, but also at the interface of robotics and environmental sciences and sustainability sciences. So I think if you combine these three pillars, materials, embodiment, robotics, and autonomy, with environmental sciences and sustainability, I think then we have really something that can really improve the world. So thank you very much.
Thank you very much, Professor Mirko. And it's good to see multidisciplinary aspects, they come along. And please stay with us once we finish for the session of the questions. Thank you very much again. So we would like to introduce our elite professor, Professor Naira Hovkimian. She is a professor within the Mechanical Science and Engineering at University of Illinois Urbana-Champaign and director of the Aviate Center. She holds PhD in physics and mathematics and has authored more than 500 publications, 2 books, and 11 patents. Of course, we know her about, or she's famous about her work in adaptive control, and the platform is yours, and we are eager to hear from you about your presentation today. Thank you very much.
Thank you for inviting me here. Actually, I just got invited 2-3 weeks ago by Jorge, our conference chair, and I was surprised to be such last-minute addition to a keynote session. And just now I realized that maybe my talk will come across a little bit of like an outlier, because when I got the title regarding speeding up flying machines, because I do not come from traditional robotics community, it was a challenge for me. Speeding up what? The actual flight, the decision making, or speeding up the development of the industry to be able to have flying machines that can carry wounded patients from hurricane zones, from fire zones, be very sophisticated with the task, which does not require necessarily flying fast, but be very sophisticated with the task. So all these are questions that kind of were going around my brain. What does it mean, speeding up flying machines? So just to give you a background, because I come from this more of an aerospace community and control community rather than robotics community, I will go ahead and remind all of you of the miracle on Hudson when the Captain Sullenberger was kind of capable of taking the decision, the right moment regarding the bird strike and safely landing the airplane in the middle of a river, saving all the passengers' lives. So it's a correct decision making while flying really at very fast speeds on passenger aircraft and being able to save everyone. So safety, reliability have been the main questions we have been asking in our research while dealing with the community that deals with passenger airplanes, with human lives and safety issues on this scale. So what did help him to come up with such a decision? That's long years of experience and training of neurons in human brain that helped him to lead to correct actions. Most likely, if instead of him we had a younger pilot with less experience, he might have not taken the decision to land in the middle of a river and would have tried to reach one of the airports, which, like the simulations, proved to be non-feasible. So our challenge in our work is every day how to mimic the brain of the pilot Sullenberger and to achieve that level of autonomy, for example, for flying machines that we just saw in the prior 4 outstanding presentations. I was very impressed, by the way. The talks were stellar, and I learned a lot. Thank you for having me in this keynote. Otherwise, I was maybe not aware of all these developments in the field. So what's happening in a typical flight control? We have a multi-level adaptation or multi-level design challenge. The first layer is the mission planning. The second is the path following, and finally, there's the low-level control that has to execute these actions. From our perspective, so if we talk about the flying speeds, let's go there. How do I click here? So this is what we flew on a NASA airplane. This was a 5.5% Boeing 757. That the challenge was to hold it in stall to give the pilot few extra seconds of recovering the stability to recover the flight. And these flight tests were happening in collaboration with NASA. So there is no voice. I guess the voice is not connected, but it was apparent in other talks. So nothing is heard, unfortunately. So the airplane was flying at 80 knot speed flight condition, and when it hits the stall, the speed drops to 40 knots. And our L1 adaptive controller was being tested for these conditions to help the pilot recover the controllability. Here is the Learjet flight, where we are already flying at 250 not equivalent airspeed conditions, so you see the flight conditions here highlighted. And again, we were able to recover from accidents that are known like saber dance, in case if you have heard of it. And finally, we flew the Vista, which is flying at much faster speeds. This is the F-16 platform. But unfortunately, I'm not able to show anything regarding this because of the nature of these flight test deployments at Edwards Air Force Base. So since the voice is not here, and the voice is what makes it all exciting, I will move forward to the next slide and say that moving from that world of aerospace to the world of robotics, one of the first projects that we had to do with elderly care. Like I said, this is already about flying very slow to help elderly to age at place, while at the meantime not scaring them. Like, for example, a pill delivery could be done with a phone prompt and helping people to age at place, because it's projected that by 2040 the population above 65 doubles, and there won't be enough young people to help with assisted living facilities. Developing technologies that can help people to age at place can be instrumental to facilitate and simplify the life of people who may be in need of some extra assistance. And the inspiration was coming from this Cinderella movie, where kind of the birds start washing her, and as you see, all the challenges appear to be control challenges. They need cooperation, they need communication, because there can be weight changes and other challenges. And finally, the perceived safety that I want to emphasize, that physical safety and perceived safety are different things. While physical safety in engineering is just the lack of collision, put it simply, humans' perceived safety can be different. What you see here, the student has designed the drone to stop within half a meter from him, but every time the drone approaches, although he knows the drone will stop, he is still scared of it. So the lack of perceived safety may lead to mistrust to robots, and if we want them to help in emergency response situations, so having trust in them is critical. And here we leverage virtual reality type of technologies to test humans' perception of safety using galvanic skin sensors and similar experiments. So moving forward, here are a number of flight tests of our lab. This is Learjet with engine out simulations. This is that VR experiments. This is flying the Alpha Pilot simulator, but I don't know why they go black instead of showing the movies. So if, okay, they are all starting one after another and turning black. So we had the Alpha Pilot simulation put by Lockheed Martin and MIT, what you see here, where the drone, it was the drone racing competition that Davide Scaramuza presented, where they came across as champions. So we augmented the L1 adaptive controller around the model predictive path integral controller that was designed by Georgia Tech, just to show that we could clear more windows in this race and add to safety. So the L1 adaptive controller was also tested here on the Learjet that we don't see here now, and there are other approaches. You can find some of these movies on our website. So looking into our reality, we are now living the 5th industrial revolution, when already the key challenges are coming, boiling down to interaction of robots with humans and how these robots could be customized to meet human needs. So while the drone racing is indeed important, it proves feasibility just in the rich sense of aerodynamics, what type of motions are possible and what type of speed conditions are possible. We still need to be able to address the societal needs, be around humans, and help them to safely interact without feeling any concerns regarding their own safety. From the perspective of theoretical challenges, as we move into this dynamic and rapid world where the data, the real world data, usually happens to be different from the training data distribution that's being used in some of these learning algorithms, our work theoretically has moved into the field of distributionally robust adaptive control, where we are trying to quantify the robustness margins in terms of distribution shifts and specify bounds in terms of Wasserstein metric, maintaining the actual real data distribution in a tube around the nominal data distribution to ensure the safety of the operations. And looking into future, I think everything will be going towards space robotics, where we'll have to move in really harsh environments on Mars or on Moon. I had a capture here from Interstellar, but unfortunately, again, the movie doesn't work. And where the space manipulation, space construction, space agriculture will call for new methods, so where we will need to deal more with unknown unknowns as compared to known unknowns, and be ready to tackle challenges, talk about robustness of these solutions in these unknown environments far away from us, and be sure that whatever we design here on Earth would be useful for space exploration to tap on space economy that's rapidly growing. Thank you. I'm sorry that the movies didn't work out. It's not my laptop.
Thank you very much for the inspiring presentation, and you see the full scale of implementation. And before maybe you will join us, I would like to ask you while you are in the stage, so what's your view about the adaptive control L1 or L infinity and the reinforcement learning perspective, and what's your view on this? Thank you. And you have the mic, please, if you want. Yeah.
There was a question for me?
Yes.
I'll tell you, nothing is heard when you talk here.
No. So my question about what's your view about adaptive control, L infinity or L1, and reinforcement learning from your perspective. Thank you.
Okay. So we did look into reinforcement learning approaches, and we do have experiments on those on our website. And the experience shows that when the environment changes, some of the reinforcement learning methods may lose robustness when they face new data that has not been used during the training. What we did, we augmented those with our L1 adaptive controller to ensure robustness for the new environments that were not present during the training. We had a paper this year in ICLR, or last year in ICLR, where we showed how this augmentation helped to tackle the 5 benchmarks well known in this community. I think it was presented in May in Vienna. So that's my answer.
Other aspects also, what's the comparison between control of full-scale aircrafts like F-16 and others and drones, small-scale drones?
Oh, the difference is that when you deal with the aerospace community, it's a lot more conservative. It's not like the robotics community where the innovations can be easily tried, tested, and you can have fun in that process. With aerospace community, it's long, it's very slow, it has to be certifiable, and the way they progress, for example, when we go to NASA to fly the subscale Boeing, or we go to fly the Learjet, we go, say, with 100 different scenarios and failures that we are ready to try, test. We are sure, because we have worked with the simulators, with all the data that was provided to us. They will only pick and test 10. There are people on the board, they just can't take the risks, and every time they add a little bit of more uncertainty to test how well you can take it. Well, I'm proud that we were able to fly into stall and post-stall, to fly through engine failures, to fly through very challenging scenarios where they historically had cases of accidents, and we were able to save those. It's a different community with a different dynamics, and not to mention that 20 marshals and generals have to sign some papers before you fly a plane with a man on it. So it's a different process just.
I would like to take also the panel view about future of reinforcement learning in the paradigm of control from low level to medium to high level, from low level control, navigation, and guidance. What's your view on this? Thank you.
So, in my opinion, is not replacing optimal control, as we still are lacking generalizability. For example, in the tasks that I've shown today, like the racing, every time that you change the racing track, you have to relearn from scratch. We tried, actually, not relearning from scratch, but for example, from initializing the weights from where you were before. But eventually, if you don't want to just learn to fly, but you want to learn to race as a champion, a human champion, well, actually, a number of iterations are kind of the same. Where actually, I would say, learning from an amateur level performance really makes sense with respect to learning from scratch is when you don't do state-based RL, but you try to do RL directly from pixels. And we are not there yet because it's computationally very, very, very inefficient. Just to give you an idea, in the Nature paper, I told you that the training time is 10 minutes. The state of the drone is still explicitly computed. It's computed with visual inertial odometry, which we know how to run. Then we tried actually learning directly from pixels. Well, it doesn't work. But it works if you lift the image into, for example, another abstraction, like a latent space. And there, actually, the training time goes up from 10 minutes to 24 hours. Now we are making progress on this, and the paper that we are going to present at CORL shows that if you bootstrap reinforcement learning with imitation learning, now you can make this feasible in a few amount of hours. But we are still talking about hours. So we are still very far from how humans are actually able to learn, and also generalizability. With regards to generalizability and sampling efficiency, I think we need to reconcile MPC and RL. I showed a solution of basically putting a differentiable MPC in the last layer of the NMLP and training with reinforcement learning. And this provides now generalizability, robustness. We can achieve the same lap time as RL. The only thing is that differentiable MPC at the current state of the art is a bit slow.
Thank you.
Yeah, I think it's a very relevant question. And indeed, what we have been doing is, of course, replacing certain components with neural network. But yeah, so originally I'm from an AI background, and most AI persons would love to do tabula rasa, actually. So one big network trained end to end. But as roboticists, we experience when we try this that this is a bit naive, right? And I think actually that robotics can play a role in discovering what elements should be prefixed or not, like nature versus nurture, right? It's a huge debate in biology. And I think that working with robotic systems, we are in a good position to actually contribute to that discussion. And for example, the brain is modular, and I think having modules will really help. Much of it can be like predetermined. But we also know that each drone, for example, has a different weight, the motors are different, etc. So there are some things that you want to adapt online. In the same vein, objects in your environment can have a very different appearance. So a tree here in Abu Dhabi is pretty different from the trees I have in the Netherlands, right? So, but we learn that during our lifetime, and we do that without supervision. And that's why we look not only at reinforcement learning and simulation and then porting to reality, but we look at learning algorithms that can work directly in the real world, like self-supervised learning.
Thank you. Giuseppe, please.
I think the main issue is that, for complex systems, like, for full dynamics, as we show in one of the papers, it's very hard that the exploration that starts from, the top level goes really down to the lowest level. So at the end of the day, I think reinforcement learning has shown very promising, for simple systems. If you think, more toward the planning level, and that has been the trend, for example, in multi-agent systems. So very good, promising results, but still on point mass, basically agents. Once you really scale to the full dynamics, it doesn't, perform as well as a combination probably of an optimal controller with basically a reinforcement learning algorithm that runs at the planning level. Classic example is, all these exploration algorithm that works pretty well, in simulations. You can probably let them work well with simple dynamical system, but as soon as you want to go with full-scale dynamics, that doesn't scale basically anymore.
Okay, thank you. Any of you, please, Professor Naira?
So I think I answered your question in the beginning, right, regarding...
Let me to segregate this one in this way. So do you think usually for low-level control, we adapt physics-based? And for medium, high level, then we may do hybridization between them. For the medium, which is the navigation. For guidance, it will be reinforcement learning, where the system will learn from the environment. Or do you think otherwise?
Sorry, I didn't get the question. It's just...
So the question I ask,
to come close.
because we have three paradigms: low level, which is normal control we use with feedback, adaptive, robust control, all of these things. We have navigation, which is medium, and sometimes we combine low-level control with reinforcement, and we have guidance in high level, and we can use maybe non-supervised or unsupervised paradigms or reinforcement learning. So do you think this is the way, or do you think this physics-based should be involved in all these layers?
I think it's very much task-dependent and mission-dependent. It depends what is your objective. If you were in Captain Sally's position, you did what you could, right? If we're talking about developing drones for agriculture or for emergency response, these are different objectives. For agriculture, it's about sensor richness, sensor data that can give you clear image of the critical needs of the crop. When you talk of emergency response, it's a different issue, like you have to be able to deal with wounded people and so on. So what's the future? It depends upon the task and the mission and the industry. It's very different, because it so happened that I worked with different industries and different communities, from aerospace to robotics, saying that this is the future, is the wrongest thing to do. It's very different, and industry-specific, task-specific, platform-specific, sensor-specific. Given your limited computation on a small platform, how much you can accomplish. Nobody can say reinforcement learning is the best or optimal control is the best.
Yeah.
It's not a method competition race.
I totally agree with you. It's driven by the application and the needs. Thank you very much.
I think an important aspect, is what kind of abstractions and representation David was saying as well, and I tried to show in the presentation. You select for solving your tasks that are meaningful, and this matters both in optimal control and reinforcement learning, and that was the key that actually made RL to work in this case.
Yeah, I agree. So Mirko, are you with us?
Yes, I'm completely
So let me jump to a question to you regarding, because usually if we have tasks, we do synthesis in order to come up with the system to do this task, if it doesn't exist, the system from the first place. So then introduction of physical intelligence from your side and your team. So can you elaborate a little bit what the future of AI and physical intelligence, and in order to achieve systems, they are optimized for certain tasks, or they are generalized for several tasks? Thank you.
Yes, thank you. That's a very important question, I think, because often what we do as a robotics community, I think, is we build a robot and then we try to find an application for it, right? So it can do this and that, it can do mapping, for example, and this can be valuable. Now, however, nature doesn't necessarily function like this. There's not one task that the natural system has to fulfill. It has to be able to fly, it has to be able to interact with the environment, maybe move in air, move in water, move on ground, also reproduce, find food, build its own nest. And this is a very broad and much wider kind of mission set or requirement that the natural system has. Now, because of that, it's able to really, live outside and actually be resilient to the unpredictability of the natural environment. And I think that's the key. So how do we really create artificial life? Systems that have intelligence embodied not just in their kind of nervous system, in the sensor or in the interaction, how sensing data is processed, but also in their morphology, in their embodiment of the materials, of the interaction with environments and with other agents. And I think that's generalized AI, maybe, or lifelike AI could be the future for robotics. And for doing that, I think an opportunity is to move away from the concentration on vision as a primary mode of interaction or environmental sensing. An insect doesn't just use vision, it uses tactile information, it uses aerodynamic information, it uses acoustic information, and all of this, it then processes it in its own perception and learning, but also it then adapts its body and grows accordingly to have capabilities of certain functionality that it can do. So I think if you take a wider approach to intelligence, a multi-sensory approach to intelligence, and integrate it with metamorphosis and with physical adaptability, then I think we have a big opportunity to achieve systems that are really intelligent.
Thank you very much. I have last things for Guido, please. If you can give one sentence about the future of neuromorphic computing, including perception and the processor, please.
One sentence.
One sentence.
It's going to rule the robotics world.
About the neuromorphic, future.
Yeah, I mean, it's, to be honest, I was in Capocaccia this year, which is a neuromorphic workshop, and even there, many people working on neuromorphics. There's large discussions on, what is neuromorphic actually exactly? Does it need to be analog or digital? So I think it's an extremely promising technology, but we're in a stage that we're really very much exploring, and we need to start showing real-world advantages. And this is also the reason that I look at this together with our lab that's quite applied. We really want to show, okay, you can get really small neuromorphic sensing and processing, low weight, low power, extremely quickly, and we want to show that with agile flight, because as David said, it's a huge challenge in which you can make advantages beyond the frontiers of robotics.
David, please.
Yes, I agree with Guido. When we talk about neuromorphic, we need to distinguish between sensing and compute. So, for example, neuromorphic sensing can be done with event cameras. By the way, if you didn't know, there are more neuromorphic sensors than event cameras. Like the SCAMP, for example. So they will not replace standard cameras. That's a question I usually am asked, because they are complementary to standard cameras. So we must make this clear. Standard cameras are sensitive to slow movements, you know, to the continuous components of the visual signal, while event cameras are high-pass filters. So they convey the varying component of the visual signal. So they are perfectly complementary. The key advantage of the event camera is that it's the only vision sensor that allows you to have an arbitrary bandwidth at an arbitrary latency. You cannot get this with a standard camera. Let's make this clear. If you want to have a 1 millisecond latency with a standard camera, you need a 1000 FPS camera. The problem, though, is that you're going to have a large bandwidth. So typically, when you buy a camera from your favorite camera manufacturer, you choose the resolution, and then you can tune the frame rate. But when you tune the frame rate, you move along the bandwidth latency curve, because bandwidth is inversely proportional to the latency. The event camera allows you to pick an arbitrary latency at an arbitrary bandwidth, and that's a great advantage. So you can enable a lot of things, like the ones that me and Guido showed in all these videos, because it's not that you cannot do the same things with the standard camera. Of course, you can dodge balls with a 3 millisecond latency with a standard camera, but then you need a 300 frames per second camera. And what I showed at the very end, in this new Nature paper, where we basically do interframe object detection with an event camera, we do this with a latency of 0.2 milliseconds. To do this, you need a 5000 FPS camera. So what's next? What are applications? Guido is perfectly right. We don't have yet clear applications. We are exploring. We are researchers. But I can tell you that there are already some interesting specific applications where actually neuromorphic processors and cameras shine. You should go to the booth of innovation here, which is basically the world leader in this. And basically, they have found a niche application for door openers, people counting. You know, they have this 1 milliwatt spec processor that includes an event camera and the neuromorphic processor at 50 hertz that requires to change the batteries every many months, or rather, every few weeks. So this is actually what we are talking about.
Yeah, thank you very much. Thank you for the audience. If you have, please, any question from the audience, we can take. Please, yeah, go ahead.
Thank you a lot for the presentations. I have noted down my question. It is concerning the sustainable robotics. So it has been mentioned that there is a need to find a way for robotic system to be integrated into the nature themselves and not to be focused on the vision only. So the question is about the balance between predefining which sensor robotic systems to use and in which way they are integrated into the nature versus robotic system to learn themselves which sensors are the best to use and in which way to be integrated by the self-reflection. Thank you.
Great, thank you very much for the question. So
yes, please, we have only 1 or 2 minutes at most. Please, if you can close up quickly. Yeah, please.
Of course. And that's a very good question. In the long term, of course, it will be an integration of all sensing modalities. But I think in the short term, I I would suggest to include vision, auditory information, and proprioception on the body morphology to really sense the state of the body, because it shouldn't be rigid. And by being metamorphic and adaptive, I think there can be a lot more interaction with the environment. Thanks a lot.
Thank you very much. We close our session, and I would like to thank our elite colleagues. They have presented the marvelous progress in the high-speed flying machines. I would like to also to thank the audience, the IROS, all the organizer, Khalifa University. Thank you very much, and thank you again. Thank you.